Okay, so it looks like the recording is on, and why don't we go ahead and get started? So here's our kind of our agenda for the day. We've really got a couple of different topics: torque and moment of inertia, and to a lesser extent, I may put off the discussion of angular acceleration until Wednesday because it's a little more, it's not as directly related to your homework problems as some of the other topics. There were a lot of questions in the PCCI today about stop and think 12.4. So we might not get to that today. That might be on Wednesday because that's to do with angular acceleration. But since we're going to talk about torque and moment of inertia, it's also to do with those. So this will at least help us get better prepared for that. I wanted to do at least one example problem for torque because there's a problem on the homework about that. And there's one about moment of inertia. And oh, I meant to not put angular acceleration here. I meant to put rotational kinetic energy. That's going to be the other thing. We just spent 2 chapters talking about energy approaches to solving problems, and it turns out for rotation problems, the energy approach is actually pretty straightforward for solving problems. Okay, and the slides are at the tiny URL. I'm using the same pattern I usually do, all lowercase, PHY117, chapter 12, day 1. Okay. All right, so let's go on. Let's get started here. So my big picture slide is actually, there's only one big picture slide today. And that is that, chapter 12, we're not necessarily introducing a lot of new ideas other than, I would say, moment of inertia and torque. Those are kind of 2 big ideas. But they sort of fit in a big framework that we've already been building and what we've been building kind of all semester. That when we want to describe motion, we talk about position and velocity and acceleration. And earlier in the semester, we talked about how the analog for position would be like theta. Like you'd mark some location on an object and it rotates, and where is that angle theta in a coordinate system that's at the center of rotation. So theta was the rotational equivalent of position. For velocity, it was omega. This was in radians. Omega was in radians per second. We had acceleration, which really had 2 kinds. There was centripetal acceleration, which was in meters per second squared, but you also had rotational acceleration, right? And that was in radians per second squared. And in a way, this chapter, rotational acceleration, could be kind of conceptually a little bit more important now, because one of the things that we'll get to eventually is that, what causes angular acceleration is any force that provides a torque can provide some angular acceleration. So that's kind of the one thing we really kind of glossed over in the past was, oh, well, what's causing this angular acceleration? And if you had asked me that directly, I would have said, oh, let's wait till chapter 12. But here we are, we're at chapter 12. What I think this chapter, what I hope this chapter has helped you see, and I hope this puts it in a good perspective, is that there is a rotational equivalent of force, and that's what torque is. And I made it with a fancy hatted T because it's really kind of like a Greek letter tau. And the Greek letter tau is just what's traditionally used. Torque, Greek letter tau. And it's sort of the rotational equivalent of force. It's the thing that makes something rotate faster and faster or slow down. It's the thing that will actually cause you to have an alpha and therefore to cause omega to change, right? For mass, the equivalent is called moment of inertia, which is 3 words. It's going to take me a minute to write. Moment of inertia. And to the extent that inertia is like mass, moment of inertia is like the rotational equivalent of mass. I often abbreviate it as MOI, and if you looked at my comments on your PCCI questions, I often put MOI in there for moment of inertia. But when we're using it in equations, we usually just use letter capital I, okay? There is I mean, you can imagine any object that's spinning, it took some energy to get it to spin, right? So that spinning, it's actually the motion of mass, right? So there is an equivalent to kinetic energy that just takes into account the fact that the mass itself is rotating. And that we'll usually call K ROT for rotational kinetic energy. And like so many of these, there's just, there's equivalents. We had in the past a 1/2 mass times velocity squared for K rotational. Well, it's going to be the equivalent of mass, which is moment of inertia, right? Times the equivalent of velocity squared. Well, omega was the equivalent of velocity squared. Okay, and so we can do things with conservation of energy, say, or work kinetic energy theorem. We can use all of our energy ideas in rotating systems as long as we are willing to acknowledge that rotating objects have a kinetic energy just because they're rotating. Now, if they happen to be translating as well, they'll still have translational kinetic energy that would be the 1/2 mv squared. But this is going to be very powerful for solving what might seem like a really complicated problem in a fairly straightforward way. And of course, Newton's second law, there's an equivalent to that are torque net. So if you have more than one force acting on an object, whatever torques those forces cause, you add them all up. The equivalent of mass here would be moment of inertia. And here, since we're talking about rotation, the acceleration we're worried about is alpha. Okay, it's whether that rotation is getting faster and faster, or is that rotation getting slower? As if it's starting from rest, which way is it going to start rotating? Okay, so this is kind of the big picture. And what I want to do today, I think the things that are most unfamiliar based on your PCCI questions is this. Moment of inertia is one big thing. And torque, I'd say somewhat to a lesser extent. But for torque, there's how do I use that in problems? That did come up, and people were asking about examples for those kind of problems. All right. So there's my big picture. So I'm going to start off with torque. Okay, and I think of torque as sort of the rotational effect of a force, right? A force can cause a torque, or won't have to cause a torque, but can at least cause a torque. And it's kind of a measure of how much does the force tend to rotate an object about some axis. So I'm going to underline this about some axis, because that axis turns out to be really, really important. Now in your book, they talk about the vector cross product. We had done the vector dot product last week. And this week we got the vector cross product. So they said something like tau is r cross f. That means tau itself is a vector. And kind of, since we're really sticking to sort of the 1D equivalent, tau is really going to be something that indicates clockwise or counterclockwise. So I'm not going to worry that much about the direction of tau for the moment, but it's r cross f, and your book also says, well, that is magnitude of r times the magnitude of f times the sine of the angle between them. And then your book also says, but if you look at something called the, what did he call it? The line of action. Okay, and you can tell because I don't remember the term so readily. It's not one that I use very often, though some engineers do use it a lot. They say that D times F, where D is the line of action. The other way your text does it is they say basically it's that, you know, it's that magnitude of R times F tangential, or magnitude of, see, if we're just looking for magnitudes, and I'm going to come back here, or at some point here, let's see it maybe here, and I'm saying I'm really just looking at the magnitude of tau right now. That's how I'm going to be trying to find it. Now, there's 3 ways to do it. Does it matter which way you do it? No. If you're already familiar with one of these ways, do it that way. Because of the way problems are normally presented, I honestly think that this last one is actually the easiest way to do it. Okay, but and I've got that on the next page. But let's talk more about this definition. We need it's a cross product of vector R and a force F. So what the heck is going on with those things? Because you'll have a problem where you might have this axis of rotation is so either given or implied. And then you'll have, say, some force that's acting at a particular location, right? So that blue dot is supposed to represent where that force is. It's like a piece of string maybe tied onto something. You almost never see this vector R drawn on the picture. You will have to supply the R, okay? That's now on your plate. You got to supply the vector. And that vector, let's see, I put it in green here. Oh, in fact, I just put it over here so that, oh, no, I can't move that, can I? Okay, I'll have to draw it in then. You have to supply vector R, okay? And R is really important. You have to know where the axis of rotation is, and you have to know where the force is being applied. And you go from the axis of rotation out to the place where the force is applied, okay? Commonly, this R is referred to as the lever arm. Sometimes the book also calls it the moment arm. Some people use those terms interchangeably. But the important thing is, where does it start, where does it end? Because if you know those 2 things, you can draw it. You're all very good at that, okay? So this is a really important thing about torque. You know, even when we did work as a dot product, we mostly just cared about, you know, the magnitude and the direction of these force and the displacement, say, for work. But here, now we have to keep track of the location where the force is applied, because that's going to be critical to us being able to draw the right vectors, okay? So I can't emphasize this enough. This is a new thing that you haven't had to do in the past, okay? So I wouldn't just say my favorite way, but the way that most students I found in the past kind of get it and get it correctly is if you find the magnitude of the torque by looking at the magnitude of R times F tangential, right? And honestly, it's the same thing that we called F perpendicular in the past. But I get the same drawing over here. If I take that force vector and divide it into the force that's parallel to R and the force that's perpendicular to R, then it's really this perpendicular part that's doing all the torque. So this is by far the fastest and easiest way, and largely because the way our problems are normally presented, they're presented kind of like this, where you've got an axis of rotation, and you can draw in your R vector, and then if you have to go figure out a sine, a theta, and which angle, and blah, that starts to get tricky. But if you can just do components, which you're all very good at, you can say which component is actually perpendicular to R, because that's the one that's doing all the torque, right? So for example, let me pull up my little stick. I'm using my back scratcher as a stick today, and I got a little string here to apply a force to it. So if I were to apply a force to this at a 90-degree angle, it's very effective at helping start this to have motion. If I pull this way, it doesn't do anything about rotating, right? It just maybe might move it off to the side here. But it's most effective here. And then if it's in between, well, its effectiveness is somewhere in between. But so a part of this force is kind of causing it to go off to the side, and the other part of the force is trying to cause it to rotate downwards. So that's the real reason why I think this is the better way to do it. If you already know how to find the angles really well, then that's not incorrect. But I'm going to mostly look at it this way, with looking for what component of the force vector is kind of perpendicular to the lever arm, and go from there. As far as the direction for torque, I'm going to just describe it as clockwise or counterclockwise. So this particular force that I've drawn here, in case you can't see the arrows down on this side, and its perpendicular component here, what direction would this object rotate? Well, it looks like if that force were applied, say if it were at rest and then this force were applied, well, it would start to rotate this way. So that would rotate counterclockwise. And so there you go. The direction is counterclockwise. Okay. So the really important thing that I want you to remember about torque after you leave this class, even if you can't calculate it and have to go look up the formula for getting the magnitude, that torque depends on both where the force is applied and what angle it's applied. And those are the two most important things about torque that you should remember kind of as a concept. Okay, so let me go here. Okay, so I've got a little demo behind me here. And this is one where what I'm hoping we can do, let me stop the screen sharing, is I may ask you some questions, and I want to use either the chat. Yeah, I'm going to use the chat for people to kind of answer. So if I'm going to go ahead and pin my video so I can see my video, because its demo is right here behind me. And what I've got here is a little plastic rod. I covered it with paper. This plastic rod, it's on kind of a little axis here. I can tighten it up actually and make it stay in one place, or I can have it a little bit loose so that it's free to rotate. This rod actually has holes in it. It's got a hole. Every place where you see these little arrows here, there's a little hole here that I could put a hook, and I made some hooks out of some paper clips that I just bent up, and I've got hooks over here. And it's as if this rod has a length of 8 times little d, and these holes have a even spacing. The spacing of the holes is a little d. So we'll kind of use that. And what I think we're going to do first is just kind of, remember what torque is. I'm going to put a hook here. I'm going to take 100 grams mass from one of our mass sets, and I'm going to put it right here on this hook here. And I'm thinking about, what is that mass doing to the rod right now? Well, it's actually applying a torque. So if it's a torque, then we've got to have an axis, and we've got to have an R vector and an F vector. So what are the vectors that I need here? Well, if my axis of rotation is right up here, and I've got a mass here pulling down, then my force vector must be equal to the gravitational force that this mass is feeling, because it's just then pulling on this paper clip like a little, as if it were a piece of string. And so long as it's not moving, that force that it's applying is equal to the gravitational force And this is 100, oh, I'm sorry, this is 200. I need to do the 100-gram mass instead. 200 is going to be too heavy. The 100-gram mass. 100-gram mass times G is about 1 Newton. So I'm pulling down at this location with a force of 1 Newton. And then the lever arm, in this case, would be equal to 2 times D, you know, pointing over towards this side. And I'm not going to say right and left because the zoom gives me either a mirror or not a mirror and gives, anyway, I'm going to say toward me and away from me. So this has got a R vector toward me, got a force vector going down. It's perpendicular, you're welcome. So since it's perpendicular, 100% of that force is tangential or perpendicular. So I would say the torque that that's acting on this rod here due to this particular little 100-gram mass would be 1 Newton times twice D. Okay, so we've got the things we need to look for all here. So let me see. If I were to let go of this, what do you think would happen? Anybody there? I don't see anything happening in the chat. So put something in the chat if you have an idea what would happen if I let go of this end when I'm not holding on to. Yeah. Okay. Oh, good. I'm seeing a bunch of replies. I'm seeing rotate in the CCW direction. Some say clockwise, some say, I'm not, wow, here I'm not going to be able to determine what you see as clockwise or counterclockwise. But I'm also seeing people say it would rotate down on the side with the mass. Okay, so if that looks clockwise to you or counterclockwise to you, so that seems to be the consensus. It's gonna rotate so that this mass goes down, and of course it does. If I just let it come to equilibrium, it sits down there, okay? So right now I've still got this mass exerting a force on this rod. Is it producing any torque in this position? I'm getting a chorus of no's in the chat box. Yeah, and the reason being it's important not just that you're applying a force, that it's some distance, but the angle here isn't right to produce torque, okay? So if you have torque, you can get rotation. In fact, I would argue there's some angular acceleration right there. It accelerated way down. Now it kind of overshot equilibrium because I don't have, I only have a little bit of loss in the system. But if I were at a location like this, would the torque caused by this mass be the same amount as it was up here if I have it sitting here? Does that have the same amount of torque? Or would it be more, or would it be less? I'm seeing a lot of people saying less, and I'm happy to tell you I feel like it's doing less because this is less effective. A force that's at an angle, only the portion of this force vector that's perpendicular is going to be able to produce any torque. Okay, so good. It seems like you have the kind of the really important things about, you know, how to figure out a torque down. So now I have another question for you. I've got also a 50-gram mass, which I can put on a hook. And so if I were to put that on here, what if I wanted it to be kind of balanced, meaning there's no net torque? Where would I place that? And I'm going to restrict myself to the far side, away from me. Where would I place 50 grams? If I placed it at the same location, would that you know, what would happen to the rod if I do it like this? Well, I would argue I've got one torque caused by this mass and one torque caused by this mass. So in this current situation, if I were to let go of it, would this thing rotate or would it be balanced? What would happen, do you think? Okay, I'm seeing rotate, 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 rotate. I'm seeing lots of those. Okay, if I let go, it certainly does rotate. It doesn't seem to rotate as much as it did before. Okay, and so why is it that it's still rotated? Anybody have a quick explanation? Why does it still rotate? I put a mass over there. One is because someone's saying the masses are different. And oh, things are going past faster than I can read them. So what I'm really happy to see the word torque coming up in many of your responses, because I really want you to think about the problems in terms of torque as much as possible, even though the torque in this case is being caused by masses. Okay, that there's that intermediate step of thinking about torques. Okay, and I think someone had said, well, they say the net torque is not zero. The torque is different. The torque that's going away from me, meaning maybe the torque due to this one, is only half as much. Oh, good. Someone says the R for the smaller mass has to be greater for R than the larger mass. Okay, so I might do better, you're saying, if I go out a little further. So if I go out a little further, still not balanced. Let me have to stand up for this one. I put it out as far as I can here, and I'm going to actually just bend this a little bit more to keep it in place there. So if I do that, it sure does seem like that balances. And I think a couple people so far had said, yeah, you need to put it out there twice as far away because it's only half as much mass. So the product of R times F has to be the same, because this one will cause a torque kind of sending this side down toward me. If it weren't balanced by the torque caused by this 50-gram mass, that would make this arm go down on the other side. Okay, so good. And this is, of course, the way mass balances are the physics that a mass balance is based on. So good. It sounds like understanding a net torque is something that you've got pretty well. So I want to do one other thing with this. I'm going to take off my masses here. And what I'm going to do is, I mean, 4 is not enough. I would like to have a little bit more freedom here. So what I'm going to do is I'm going to put the axis over here. All right. Okay, and I'm going to put let's see, I'll put my 100-gram. Oh, where should I put it? Which side should I put it on? Yeah, let me put it on this side. I suppose it doesn't matter too much. No, actually, I changed my mind. I'm going to put it on this side. Okay. I've got my 100 grams sitting over there. All right. And I've got my 50-gram ready to go. So my question for you now is, where should I put the 50-gram if I want to balance that 100-gram? Okay. Think about that for a minute, and then go ahead and put your answer in the chat box. And I'm going to hold it here. Yeah, I see one answer is 4D from the center. And is that from the center toward me? Because the next person says, put it on the same side as the 100 gram, meaning put the mass over here someplace. Okay. So I think those, I don't wonder, Laura, did you mean to put it for, because there's no 4D on this side, so I assume you must mean on this side. Okay.
Yeah, but did I misunderstand the question? You're looking to balance it.
Yes, I am looking to balance it. Yes.
Okay, then yeah.
Okay. I've only got 2 people giving me any feedback in the chat, unless I'm missing something in the chat. 4D on the other side from the, right, on this. So you're saying here. And someone is saying on the same side as the 100 gram. Does anybody else have an opinion here? I guess I don't really mean opinion, because in physics, we seldom give opinion questions on our quizzes. Our questions are a lot more like, if you're going to give an opinion, it better be well informed by some physics backing it up. So maybe this is something where maybe I should send you to a chat room. Think about it a little bit more. Tell me what you're, I don't want to go forward with just like 1, 2, or 3 people engaged here. And if there's something where it's like, I don't know, what's the question you would need to have answered to be able to say? Oh, okay, so here's a question. Does having the axis so far over add weight to the side? Oh, very good. The mass of the ruler. Oh, Piper wants to know the mass of the ruler. Megan seems to be worried about the mass of the ruler too. I guess it should be less than 4D since the bar isn't massless. Oh, okay, okay. Well, what would we need to know about this, about this ruler to know what torque? I mean, could it be exerting a torque? Well, there's one easy way to find out. I'll take my masses off. What happens when I let go? That looks like it might be on a little bit too tight. It surely does rotate, and it rotates quite freely. So even with no masses, there's clearly a torque, and a relatively big one. The one thing I can tell you is that I have a little kitchen scale in my kitchen, and after I taped all this paper on here, the mass of just the rod itself was 135 grams. So if we multiply by G, that's going to be about 1.3 newtons of force. If I wanted to account for that, where would I place, like, where would that force really be occurring here? Oh, yes, I see. I've got a question about what is this little d that we've been talking about. I wonder if I can move this a little closer so that it's easier to see. On my ruler, there's 1, 2, 3, 4, 5, 6, 7, 8 little segments, and there's a hole there. And I've got a little d written on all of these, but maybe the d isn't so easy to see on the screen. So, so thank you for that. Yeah. So yeah, so how would I do that? How would I take into account the fact that this rod by itself, by the fact that there's more mass over on my side compared to the far side? How would I take that into account in thinking about this torque? Does anybody have an idea? They can guess. I'm not keeping track of who guessed what in the chat box. Does anybody have an idea? Okay. Oh, okay, so see, moment of inertia is coming up as a possibility, and there's people talking about how much of the mass of the rod is on the left compared to how much is on the right. Um, someone mentioned a term, gravitational torque. Another person said we need to think about the center of mass, and how far from the center of mass the axis is. Okay. Okay, right. So we haven't really talked that much about center of mass, but you read a bit about center of mass. And for simple shapes like this, center of mass it's often the same as the geometric center. And for a rod, the geometric center is pretty easy to find. It would be the center. Okay. So the center of mass is right there, and I'll put a great big dot next to that one. And I'll write the letters CM, which I don't know if they'll be quite visible. Okay, I've got my center of mass there. I know what I'm going to do. I'm going to bring my whole experiment forward a little bit for now. Okay. So I've got my center of mass here. I've got my axis here. And there's a distance, which in this case is 2 times d. Right? So 2 times d. So center of mass, the interesting thing about center of mass is that you can treat it as if all of the mass is here. So if I took it's sort of the equivalent of if I had a 135 gram mass and hung it here, and this rod were actually massless, then it would have the same effect. So we can treat this rod as if all of its mass were sitting here at center of mass. So I have the equivalent of 135 grams times G, so about 1.3 newtons down on my center of mass. So if I have now 100 grams sitting here 2D away, and I've got the mass of the rod acting here at the center of mass of 135 grams. So 1 newton pulling down over here, 1.3 newtons pulling down over here. What should happen if I let go? Okay, so I'm seeing it would rotate. Now, which way is it going to rotate? So is it going to rotate so that like I would get hit in the head there? Or is it going to rotate this way? Maybe let's say, would the 100 gram mass go down, or would the 100 gram mass go up under the current conditions? So the long side would rotate down. The mass is going to go, I see all kinds of answers. I'm seeing the mass would go up. I'm seeing the mass would go down. Now I'm seeing more of the mass would go up than the mass would go down. All right. Should we just try it and see? Let's see what happens. Yeah. Yeah, the mass goes up. Mass goes up because I actually had a bigger torque caused by the mass of the rod itself. And there's more than one way to do it. It's a fairly simple mathematical way to do it, to say, well, where's the center of mass? And pretend like the entire mass is hanging from there. But the person who said, oh, there's some mass on this side, some mass on this side. There are other ways to correctly work the problem, but I think that's a really good one. So now let's go back to my original question. Where should I put the 50 gram mass if I actually want this to not rotate, if I want it to balance? Should I put it on the side towards me, or should I put it on the side where the 100 gram mass is? Yeah, yes, excellent, excellent. And I don't know exactly what distance. I might have to kind of, sorry, I just dropped my mass. There we go. All right, so I put my mass on, and I feel like that would be too far. Oh, maybe not. Let me put it a little bit closer. Oh, I think I'm getting close to it being balanced. So I actually had to put it almost as far, and that kind of makes sense because if this was 135 grams or 1.3 newtons, and 100 grams, then that would be 1 newton, and 50 grams, that would be a half a newton. I've got to apply almost a newton and a half, really 1.3 if that was all out here, but it's actually just a little bit closer, so that that half newton is not quite as effective, and it balances out nicely here. Okay, very good. I've got one last thing to ask you about, and I think for this one, I might want to put it over here. I'll put the 1 newton right on top, or maybe not even that. Let me do this instead. I'll do it without a mask because I think that'll be simpler. I've got a force sensor, and what I'm going to do is I'm going to take this force sensor and I'm going to put it on here, and I'm going to take it and I'm going to apply it right here to the center of mass point, and I'm going to pull up like this. I'm going to hold it up using the force sensor, okay? So my question for you is this. How much force would this force sensor be reading at this point when I'm not touching it otherwise and I'm just holding it steady, okay? So while you're thinking about that and putting your answers into the chat box, I'm going to set up, share my screen with Logger Pro, and so we can actually just do it. Okay. Okay. So let me get my force sensor. I'm not seeing my screen properly, I think. Oh, there it is. It's down there. Okay. I'm gonna move that up. There we go. All right, so I'm gonna hold this in place, and I'm gonna go 0 the sensor, because there we go. I'm gonna 0 the sensor in the position that I want to use it. Okay. So in the chat box, I'm seeing 1.3 newtons. I see someone agreeing with 1.3 newtons. Another 1.3 newtons. Can anybody explain? I've got at least 3 people who think 1.3 newtons is good, and maybe there are more people who just haven't typed in why they think 1.3 newtons is good, or if they have a disagreement, maybe they're just trying to be nice and not disagree. But could somebody unmute yourself and say why 1.3 newtons might be a good answer here? So Claire, can you unmute yourself and say something?
Yeah, I said that it has to equal the force that is like the force down on the center of mass. That.
Okay. All right. So let's see how that works. How about, okay. So when I do that, what do I get? Oh, I'm getting pretty close to 1.3 newtons here. Maybe a little bit higher. Okay. But I was, okay. So let me ask another question. What if I don't apply that force at the center of mass? What if I apply it out here, let's see, 1, 2, 3, at 4D away? How much force do you think it's going to take to hold that in place if I do it out here instead of doing it over here at the center mass point? Okay, I think I've got one person venturing an answer of 1.3 divided by 2 with a question mark. Someone says definitely less than 1.3. Okay. So what's the reasoning why it should be less than 1.3? So I think that was Anna. Anna, what was your reasoning for saying it's definitely less than 1.3? But actually you have 2 question marks, so maybe you don't have a lot of confidence in that answer.
I'm thinking that it could be less because there is now a distance between the center of mass and where you're putting like the force. So that's going to get like the torque thing is going to be larger because like the force required now is going to be less because there's a component R that we're multiplying using.
Okay. So I'm seeing good, some more comments. I'm saying the lever arm is longer. Oh, what a great way of putting it there. So what does the lever arm out here being longer actually do for you? It means the lever arm for this mass of the rod is stuck here at the center of mass. That lever arm is going to be 2D no matter what I do for the mass of this rod. But if I can move my force over, I can have a longer lever arm. So that means my force is going to be more effective at creating torque. So it won't have to create as much torque as it would when it's back here. Okay, and someone has suggested it's a factor of 2. Why a factor of 2? I think Megan had that with a question mark. Megan, why did you say a factor of 2?
Because force is impacted by distance, and so if you double the distance, then or the torque would increase by 2, I think, or double.
Oh, okay. Yeah, because I still need the same amount of torque to counteract the mass of the rod, right? But if I double the distance, I only need half as much force to provide the same torque. No, let's see if that's at least approximately correct. So let me go here. I'm getting about half of what I had before. I was getting between 1.3 and 1.4, and I'm getting about 0.7 now. Okay. All right. I have one last question before we give up on this. So I'm going to hold on to this for the moment. If instead of pulling straight up like this, what if I pull at a 45-degree angle? Okay. So if I pull at a 45-degree angle, will I need to provide a bigger force, a smaller force, or will the same force work? Okay. So think about that for a moment. And then when you have an idea, go ahead and put it in the chat box, okay? So the idea is I'm gonna pull on this at a 45-degree angle this way. Okay, great. Oh, thank you for answering Jackie's question. Bigger force, bigger force, bigger, 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 bigger. Because bigger is better, and that's why the answer is bigger. Bigger force since the angle is less effective. Okay, so it seems like there's a consensus among those who are on the chat room that it has to be a bigger force to achieve the same thing. So why don't we just go ahead and put it on there and find out. So I'm trying to keep that at about 45 degrees. Now when I was up here, it was like between 0.6 and 0.7. So when I'm out here, 45 degrees, it's a lot closer to 1 Newton, isn't it? Yeah. Yeah, so if we're at 45 degrees, then it's just the perpendicular component to this force. So if you figured out the perpendicular component of the force, that would give you a factor of sine theta, sine of 45, which is about, sine of 45 is about 0.7, but you have to divide by that. Okay, yeah, I can't also see the changes. I wonder if it's frozen, because I can see 0.8, 0.7, 0.8, 0.9, depending on whether I'm up here or down here. Is the screen just not updating?
Yeah, it always says 0.012.
Oh, okay. I'm going to stop share, and then I'm going to redo the share because it's, I think it must have gotten frozen. Okay, so do we see between 0.6 and 0.7 with it straight up? Is that coming through now? Okay, good. If I go off to the side, I'm more like 0.8, 0.9, and 1. Thank you for pointing that out, because I would not ever have noticed that, because on my side it looks great. Okay. All right. Does anybody have any questions about this before we move on to something else? And I have to pull up the chat room again because I don't, it goes away each time I share a screen. Okay. Okay. All right. So while we've got our minds on torque, what I think I'll do is stop sharing that, and I'll go back to our to the slides. Okay. All right. So okay, good. We've done all of those, and let's go on to something from the PCCI. And since I asked you all to bring them with you today, did anybody bring like a stick and some masses today? Oh, good. I see some sticks and masses out there for the people who have cameras on. And I did not have a lot of questions about this particular one on the PCCI, but this is one where if you don't have it, you should find a stick, or you can just do it with a pen. If you have a pen, and anything that you can tape to the end of the pen. I could not find my little drawstring bag, so I took an old sock and put some nuts and bolts in it, and I tied a knot in it so I can put it on my back scratcher. So I'm using my back scratcher here because I tape my rulers together for something else. But you can really feel that the torque caused by this sock full of nuts and bolts is more effective out there at producing a torque than it is when it's, say, halfway. Oh, I should hold it up higher so it can be seen better, right? That, I can feel it in my hand, that my hand has to provide a lot more torque to balance this than to balance this one. And I happen to pick, I have another sock with about twice as many bits of hardware in it. So I can actually do D as well. I'm sorry, you can swap it out and feel how different it is when you've doubled the mass. So this is something that I think you should try to feel. One of the things we do if you were here is we would have all kinds of different things in the room for you to actually pick up and feel how different it is to try and hold this steady than it is to hold something like this steady or like this. And I think back on one of the first days of classes, I had asked you all, or I told you all, that by the end of the semester, we were going to understand why it is that when people carry things, when people carry the groceries, they don't carry the groceries like this, right? And they don't even carry the groceries like this. They carry the groceries cradled at the center of their arm. So the equivalent of, if this was my lower arm, I don't carry my groceries out there because my elbow would have to provide a whole bunch of torque. And that might strain my sensitive muscles on my elbow. If I have them a little closer to my elbow joint, they're not as effective at producing torque, and my elbow muscles can relax a little more. But even best, if I put them as close as possible to my elbow, they hardly produce any torque. And I can carry things a lot more easily there. So torque gives us an explanation for something that you see and you do probably every day. And now you can explain it and why exactly that's something. Okay, let's get to an example. So this is an example of what I would call a statics problem. And your book uses the word static equilibrium. It's something of a redundant term, like static means not moving, and equilibrium kind of means not moving too. So static equilibrium is just our way of being really, really sure that you know it really, really isn't moving. Okay. And for statics problems, I would say there's really two big key ideas. And I'm going to start you off with some key ideas and a coordinate system. And then I'm going to send you to some breakout rooms with not enough time to complete the problem. But what I want you to do is get to the point where you set it up and you have enough equations and enough unknowns matching that you could solve the problem, okay? But I would say that the key ideas here that are really important for a problem that's statics equals the sum of the torques equals 0 and the sum of the forces equals 0. So static, or if I put it in this way, static equilibrium. And you know, we did talk about this a tiny bit before with forces. Some of the forces, if it were 0, that it could be at equilibrium, it could be at rest. So if it's going to be at rest, it absolutely has to have all the sum of the forces equal to 0. And the sum of the torques should equal 0. Okay, so it needs both of those to be true simultaneously. So here's my key idea. And this is kind of the equation equivalent starting point. Equivalent starting point. And what that equation turns into for any given problem will be different. But this idea of static equilibrium always brings both of these equations. And for some of the forces, you know you'll need a free body diagram. But for torque, I mean, with a free body diagram, that sort of takes away all the information about where the force is applied. So what we usually do in that case is we'll do something that I'm going to call an extended free body diagram. There's no particular word that all physicists use for this, but a lot of people do call them extended free body diagrams. It's a free body diagram where you maintain the information about where the forces are applied, right? So here, I'm going to concentrate on this, this beam, and I can take that beam and let me give myself an axis as well. I'm going to make the axis here. So there's my x-axis and my y-axis. So this end over here, the left-hand side, is where my x equals 0 is. So an extended free body diagram here would say, well, I've got, let's see, what are my forces? I've got a person standing at some distance d from the end. Now the person's walking out a little bit. I'm gonna say, well, let's say they walk out some distance d. The child is, oh no, x. I want to use x for that. Sorry. We moved out some distance x. Where was the d then? So I've got the 8-foot length. Yeah, there's the d. That this is d. So I've got one stump is pushing up here with one normal force. And I've got the other stump pushing up here with another normal force. I've got the person located someplace at a distance x, and the person's mass was little m. And then the whole object with length L is going to have a, I'll call it this way, a force mg, and that would be distance d. Here we go, a distance x, okay, and the distance here for N2 would be L, okay. So it's the idea is to maintain the distance information in your free body diagram, but it's from the point of view of Newton's laws, the sum of the forces equals, oh, sorry, that came out messy. If I'm thinking the sum of the forces equals 0, that could be, in both in the x and the y direction. I've got all the force information and the force directions. I also have the distance information, so I can also figure out, well, the sum of the torques and set that equal to 0. So that's what I want you to do in the breakout rooms. I want you to, for this particular problem, set up the equations for sum of the forces equals 0 and sum of the torques equals 0. Okay, so now I have to remember how to do breakout rooms. I didn't mean to stop share so quickly. Breakout rooms. And how many rooms should I do? I'm going to do 7 because I've got 3 LAs, so we should have plenty of time to get to everybody. I'll do 7 rooms and let it go there.
Hello.
Hey,
Do you want me to go browse around through breakout rooms, or?
I was going to give them a minute to,
Yeah, I like to do that as well.
yeah.
Let them organize themselves without me there. Works much better.
Yeah.
So are you feeling like you're on pace to get through what you wanted to get through?
I feel a little bit better. I'm glad they picked up on the mass of the bar. I think that was good that someone thought about that, and that seed seemed to kind of ripple through. That was nice.
Right, yeah. You are hanging out for office hours later this afternoon, is that right?
Yeah.
And then I'm going to do it Tuesday and Wednesday. Is that what we said?
Yeah, I
Okay.
think that'll work.
Just
Yeah,
double
Wednesday
check.
we have our big Board of Selectmen meeting where we get to guess what the next step is going to be for our town budget.
Good luck with that.
Oh, yes, indeed. Well, I mean, our choices are so few. Maybe it won't be such a hard decision after all.
Right.
So, okay, might be time to go join a room. I see you're in 7, so I'll go.
Do you want to co-host me so I can move around before you take
Oh,
off?
I didn't mean to. Yeah, let me co-host you there. Sorry, I forgot about that. There we go.
All right.
I just took a quick screenshot. Can you see the question?
Yeah.
A little cut off, but it's better than nothing. We're right now just reading through the question and making our own comments because we need to process the question first.
Yeah. I think I probably when I accidentally did the stop share, that was not a great move. But I wonder what I can do about that. But you're recouping very nicely there. So
Yeah.
probably draw that extended free body diagram and then look at the force and torque. So I'll get out of your way.
It is from stump 2, which is 0.
Okay.
that is equal to like catapults.
Okay, that makes sense. Okay, so we'll say the axis of rotation is at they're like the very end.
All right.
Okay. So
Then will the line of action be x minus 5 for the person?
x minus.
Oh, wait.
Hold on. Okay.
All right. So it looks like you're still kind of sorting through the problem and figuring out, you know, which forces are doing what. Are there any questions before I go look into another room? And I'm sorry, I really feel like I hit that stop share button too quickly. I should have warned people to take a screenshot or something like that.
Is it fair to assume the rotation of axis, the axis of rotation is at the far right?
Yeah, that would be fair to assume. And this is going to sound funny, but if the thing's not rotating, then you could actually pick any location as the rotation axis. And it's not rotating around that axis either, right? So it's a funny thing to think about. But I think for the coordinate system we set up, since all the distances are given from that first tree stump, you know, on the far left, that's actually a rather convenient one for the coordinate system we set up, right? That we'll be able to know the distances where the forces are applied in a pretty straightforward way, right? So I would say you can do it in another location, but I think choosing the far left is actually the far left side is a reasonably good thing to do given how we set it up. Does that make sense?
Yeah.
Okay. Are there any other questions before I shuffle off to another room? I see Jassandra's being quiet, which is her normal way. So, okay, I'll circle back and maybe a little bit, or maybe I'll see you in the main room.
Yeah, there's only one. Okay, never mind. So basically, if we got that the initial force is going to be, oh my god, what did we say was going to be the final like force in the system?
I don't think we said. I think that we were just talking about when the net force is 0, when it's at static equilibrium.
Yeah.
Okay. All right. I'm just right. So
Yeah, you look like you're still kind of sorting things through.
just a little bit.
Yeah.
We basically thought that we need to find a sort of like force before and force after. And I just got a little bit confused about how to calculate normal force in the system, just because I'm like, this is the system the board, or just, I mean, it's the board with the person, right?
Yeah. I think you're right. You have to decide what the system is, and I think if you chose the board itself or the board plus the person, that either of those would probably be fine, because either way you're going to include mg for the person and mg for the board.
Okay.
Right? So I think either of those sounds good. So the before and after, why were you going for before and after?
Because I thought that like in the beginning, the system is at a place where like the magnitude of the force of gravity and the magnitude of normal force are basically at a state of equilibrium. And then in the end, the gravitational force kind of like overrides the normal force.
Oh, okay. Yeah. Oh, okay.
But,
So I see. So you're looking, because as the person walks, something about the I would say not necessarily the forces is changing, but certainly
It's the
something
torque
about the
that's
location of the force
Okay.
is changing. So something
Yeah.
about the torques is surely changing.
Okay. Because that makes
But
sense. I'm like,
no
the force
matter
isn't
where,
changing.
yeah. So no matter
Right.
where the person is, does that change the sum of the forces in the y direction?
It does not.
No, it does not. But it certainly changes the torques that are acting on the system. Yeah.
Right.
Yes. Very, very good. Yeah. So you're right. There's going to be some values for x for which the torque's not going to be enough to make it pull it out of equilibrium. But at some point you will get an x that is big enough to do that. So I don't know if before and after will help so much as look at what the forces are doing and then look at how that changes when the force is applied in a different place, but do that in the torque equation, because the torque equation is where it makes a difference where the force is located. Does that make sense?
Yes.
Yes. Okay, good. It's about 2:16. So I think I want to pull the class back together. So you've not had enough time to do the whole problem, but you've gotten to think about some of the important things you have to think about when you set it up. So that's what I wanted to accomplish here. So I might give you like one more minute to pull together as much as you can of that, some of the forces and some of the torques equation, if you can. Okay?
Sounds good.
Okay.
Okay, cool. So, should we just maybe skip?
Okay, how we doing over here?
I think we're calculating.
Pardon?
We're all calculating.
Oh, okay. Okay. I'm probably going to call you back before you're done calculating. But it sounds like if you're calculating, then you got something for some of the forces and another equation for some of the torques.
Yeah.
So that's good. That's as far as I wanted to make sure you got. Okay. So I think I might pull everybody back in the next minute or so. Okay?
Okay.
Hi, Joyce.
Yeah. How are you doing?
Good. I was just with other Joyce, and they're talking about the normal forces. Has this group gotten past the normal forces?
Yes, yes. And I think I'm going to pull everybody back together because I don't think I can give them enough time to solve the problem anyway, but I feel like people have now have the right questions in their head about what should I be doing with these normal forces and what should I be doing with the sum of the forces and the torque equation.
Okay.
So I'm going to call people back to the main room now, I think.
Sounds good.
Okay. Okay. So I feel maybe everybody's back at this point. I absolutely did not give you enough time to solve this problem. So don't anybody feel bad if you got yanked before you were really finished. But what I hope you got a chance to do was think about, like, what does she mean by some of the forces here? What does she mean by some of the torques? And what forces should I be and all of those sort of things. And I apologize for when I was trying to get to the chat, or sorry, trying to get to the breakout rooms, I hit the unshare my screen, and I think I should have given you a little more warning so that you could have taken a screenshot of what we had. So I apologize for that, because it might have taken you a little time to reproduce a little bit of that. So I'm going to start here, because what I really wanted you to do is be able to come up with this equation for some of the forces, and particularly I'm interested in some of the forces in the y direction, because that's where the direction for all the forces for this one are. And let me pull up something. Yeah, there we go. There's the list. So I don't know which chat room to start with, but I'll start at the bottom. And I see breakout room 7 had Megan in it. Megan, did your group get to the point of having a sum of the forces in the y direction equation?
Yes.
Okay. What did you all do for that?
We know that we have the force of the child going down and the force of the log, and then which is yeah, pushing it down, and then the two logs, the normal forces are pushing it back up. So the sum of the force, so we know that the sum of the forces is the gravitational force of the child, the gravitational force of the log, and then the normal forces of the two stumps.
Is that right?
Well, I guess the normal forces are pushing the things back up. So
okay, good. I was just checking to make sure you're really paying attention. Yeah, so it'd be minus for the gravitational forces and plus for the normal forces. Okay, and we have enough, just noting, we have enough information to find, we've got the mass of the beam and we got the mass of the child. So these are two things we know, but we don't know the normal forces. Those are two things we don't know. Okay, all right, great. So now this other one, the torque equation, I'm going to need a little bit more room for my torque equation. So what I think I'm going to do is I'm going to go put this down a little further here. So the sum of the torques equal to 0. Let me go to the next room. It was Elora and Theo. Theo, can you give me one term that you put into your sum of the torques equation?
Yeah, sure.
If you got that far, assuming you got that far.
Yeah, so we assume that like the rotation point would be in the second trunk because of like the mass. And then
so you didn't use the x equals 0 for the rotation point. You used x equals 5 for the rotation point. Is that correct?
Yes.
Oh, okay. So let me note that on the picture. Okay. It shouldn't matter what you pick for the rotation point. You should be able to do it with any, because honestly, it's not rotating about any point here, so it shouldn't matter, right? So I'm going to go ahead and put a blue dot here and say the rotation point that you have in mind when you're writing that torque equation is at that point. Okay, so what's one of the terms you have for torque there?
So for the person, for the child, we said it would be the gravity, like the mg times d minus x.
Mg times d
minus x.
Minus x. Okay. So if x happened to be bigger than d, then so now, okay, so you get that term. And did you leave it plus or minus? Is it, I mean, because that's the size of the torque. I agree, because here on the picture, here's d minus x.
Yeah. So it would be like applying in the clockwise direction for. So it would be applying it downward.
So a torque that's for a force that's applied, say, right here, would that make that log, would that make it go clockwise or counterclockwise? Just that one?
Clockwise.
clockwise.
Mhm.
Does everybody agree with that?
Oh, counterclockwise.
It's counterclockwise. Okay.
Counterclockwise.
So I think I didn't stress it earlier, but usually clockwise is negative, counterclockwise is positive. So this one, this particular term would make it turn counterclockwise. So I'm going to leave that one as a positive term. Okay. Alrighty. So basically, we're ticking off these forces and we're saying each of these forces causes a torque. What torque does it cause? And Theo has just figured out for the child, this is the torque that the child exerts on the rod. Okay? Now, it might be that you used a different coordinate system. Or you used a different rotation point. But let's go with this one. And one reason being that in these slides, I have the solution already done out for the case where it's at the left-hand side. So that solution already exists. Okay, so let me go to the next group, which is Angela, Grace, and Piper. So let me ask Angela. Angela, could you tell me, could you figure out what torque would this normal force N2 have if the rotation point is right above the second log there, the second stand? I'm not hearing anything from Angela. Piper, can you see? Can you give me a not a, I don't want to say a guess, but a what do you think would be the torque caused by that bottom, that one, that N2 in our diagram, if the rotation axis is right there above the location of that tree trunk?
We didn't quite get this far.
You
And
didn't
I'm
quite
not
get that far? Okay, that's all
sure.
right. Let me go to the next group. In breakout room 4, Claire, what would you say is the torque caused by this N2 on the log? Oh. So this is true. So let me ask a different question. If it were, if that force, if we were talking about it rotating about the x equals 0 point, what would the torque be that the force, the N2 force, the second normal force, what would that be? Okay. All right. Catherine, anybody in breakout room 4, Catherine?
So
Claire?
our group, oh, can you hear me?
Go ahead, Catherine, yeah.
Okay, sorry. I thought I disconnected. So we didn't really get this far, but I'm just gonna go off of maybe what I'm thinking.
Okay.
If the rotation point is at the N2 position, then shouldn't it be 0? Because there's no distance between that force and that point.
Yeah, I like the way you're thinking. I like that. Right?
Yeah.
Because that's what the two things that matter the most about it is where is the force applied, because that determines what the R vector is. And you're saying, well, the R vector is 0 here, so the torque had better be 0. It doesn't matter what direction it's applied anymore because that's 0. So I'm going to say, well, plus 0. I suppose it doesn't matter if I say minus 0. And let me say call this stump number 2. So this is the torque caused by stump 2. Okay, so Catherine, now that you're on a roll, what about stump number 1? What would the torque caused by stump number 1 be?
So if the rotation point is still at stump 2, then stump 1 should be N1 times D, because that's how far away it is from stump 2.
Okay.
I think.
D, okay. Now, for the bonus, and maybe I should go to somebody, to another person. No, I'll stick with Catherine until we get this term done. Is that going to be a positive torque or a negative torque? where positive would make it turn counterclockwise, and negative would mean it would make it turn clockwise.
Would it be positive?
It would be positive. Okay. So we're saying, yeah, so we're going to rotate around this second stump here. If I have a normal force pushing up over here, would that make the whole thing go clockwise or counterclockwise?
If we're just considering the force from,
yeah.
Oh, then I guess not counter, sorry, clockwise.
Yeah, that would be clockwise.
Yeah.
And clockwise, you're going to call negative.
Yeah.
Okay. So stump, oop. I don't know how I did that. There we go. There we go. Stump 1 is here. Stump 2 is that 0. And then we only have one other force. We have mg for the log going across. And I'll go to breakout room 3. So even if breakout room 3, I'm sorry if you didn't have the same location, but can you help figure out what would the torque term be? Let me go to Heather. Heather, what would you think the torque term would be for the gravitational torque of that log with big M for its mass?
Would it be 0?
Would that be 0? Okay, so what's your reasoning for 0?
I'm not so sure. I just know that when we were working with like this question, we said that I know that we said I think the normal forces would go to 0 because I was a little confused by the question, like the
yeah.
But I think that we said that the two normal forces would go to 0 because one of the normal forces is at the axis, or the center of rotation, and then the other one is just, I think, going to 0. And then so we were looking at, I guess, like the mass of the child times the distance from the center of rotation, which we have, and then the other one that we had was the mass of the total beam, I guess it would, times the distance of rotation.
Okay. So if you're going to account for the mass of the whole thing, and you would need to know the distance from the from the location of the rotation axis, where would that, where would you count that mass? Because that mass is extended, right? So where would we count as the place we measure the lever arm from?
I'm not so sure.
Okay, all right. I'll go to somebody else in your room. I see also Jackie was in your room. Jackie, do you have an idea? Even if this wasn't the way you solved it originally, if you were rotating about this stump here that's 5 feet in, and the whole thing is 8 feet long, what distance would you use for the lever arm if you were trying to figure out the torque due to the mass of the log itself?
Would it be the distance from the center of mass to the stump too?
Oh, yeah. Yeah, just like when we were using this, we considered the distance between the rotation arm and the center of mass when we were thinking about the gravitational torque here. Yeah, and in this particular picture, if one is 5 feet, one is 8 feet, their difference is 1 foot, or we could just call that L minus D. Okay, and would that torque, if the force is acting, let's see, where is the center? I put the center down here. If it's acting right there at the center, and the axis of rotation is over to the right, what direction would that torque be? Would it be positive or negative? Would it cause clockwise or would it cause counterclockwise rotation if the axis is over here on the right hand, to the right of it?
I guess it would be counterclockwise.
Yeah, because that would tend to, just that one by itself, in the absence of all the others, would make it move the other way. So Counterclockwise counts as positive. So I'd say plus the distance times the force. So that would be mg times L minus D in symbols. Yeah, now I want to kind of circle back to something that Heather said, because Heather, if their group was talking about times when the normal force might be 0, they're actually almost thinking one step ahead to try and answer the problem. I wanted you to make these two equations, and let's take a look at this. I'm trying to solve for x. That's my find. What do we not know? So unknown here is, well, x, which is something we're trying to find, n1 and n2. And here we've got two equations. And let's see, in here we know mg, we know d, we know d, we know mg, we know L, and we know d. So it seems like our only unknowns are x and n1 and n2. So as it stands, there really isn't enough information here yet. We need something else in order to be able to solve this problem. But if you think about it, as the person walks out here, at some point, it will start to tip. And the very first thing that happens when it tips is we lose contact here. Okay, if we lose contact at that first tree stump, then the normal force, the normal force can't pull, right? And if it's not in contact anymore, then what do we know about the normal force at that first tree stump? The moment it loses contact. Now, it may not have lost contact yet over here at the second tree stump, but it'll certainly have lost contact there. So I'd say at the tipping point, you can make a good argument that n1 has to equal 0. So that takes care of one of our unknowns. And now we've got two equations, two unknowns. You could solve them for x, or you can solve them for normal force 2. Okay? So I'm not going to solve the rest of the way here. However, I will point out that in the slides, which I'm posting after class, there's a solution written up. It's much more neatly than mine is written up, which gives you, this is the equation that comes from some of the forces, and then this is the equation that comes from some of the torques equals 0, and some of the forces equals 0. Okay, and then there's a little bit more algebra that goes on, and if we solve it with either kind of choice of axis of rotation, we should get 6.5 feet. Is how far you can go before it starts to tip over. Okay, so this is typically called a statics problem. It's something that, if you're thinking of engineering, this will be in your future. And the other thing I would say about it is it's kind of similar to problem number 3 on the homework. Okay, but we're now at we got about 22 minutes left, and we've got to get moment of inertia and a little bit of rotational kinetic energy in. So unless there's some more questions about this, I would like to move us along. Okay, I'm not hearing anything, so let me go on to the next idea. So moment of inertia was one of the ideas that you had a few questions about. And the definition for moment of inertia is kind of, an equation form. Looks like this. It looks like the moment of inertia I, it's the sum, and it's like you're adding up all the masses of some object. So let's just take some arbitrary object. It's got some little dot here of mass. We're saying if I were to rotate it around an axis here, then this mass is a distance r from that axis. I am going to count mass that's far away from the axis more than mass that's closer. Okay, that's the big idea behind moment of inertia. And I don't care if it's far away to the left or to the right or up or down. I don't care about your coordinate system because I'm squaring the r. Okay, so whether it's up, down, left, right, whatever, you square the r, it doesn't matter which places, as long as it's far away from the axis of rotation, it counts more, right? So this is really, to me, the most important concepts about moment of inertia. It counts mass that's really far away more, okay? It gets to do more stuff than the mass that's close to the axis, okay? So if we have any given object, it's only got one mass, but it could have more than one moment of inertia, because the moment of inertia depends on where you choose that axis of rotation to be. So you can think of it like even with just a pen. If you hold a pen, it's pretty easy to rotate this way. If you hold it by the end, it's actually noticeably harder to rotate, right? So because that mass is so much further away, right, from the place where you're trying to rotate it from. So it is completely related to torque. But moment of inertia comes with mr squared, and that's the big idea. So if I were to take an object like this box and try and rotate it around this up and down axis here, and I would try and rotate it, that'd be like rotating my pen this way, right? Or if I were to try and rotate it this way, which one of those would have the bigger moment of inertia? Well, this case has more mass is far from the axis. Okay, more mass, I'll go ahead and use the traditional spelling of more. More mass is far from the axis, so moment of inertia is bigger here, okay? In the other case, the case where it's kind of upright and the axis is rotating in the upright direction, the mass is actually all pretty close to the axis, okay? So if you're looking at two objects and you're trying to compare, or if you're looking at the same object but rotating it with a different axis, then you just think about, oh, which one has more mass farther away on average? And that will be the one with the bigger moment of inertia, okay? This is a question that a lot of people had a lot of questions about. And so I took two of my rulers and I taped them together so they would look like this. It's kind of, you can do this whole problem thinking about how much mass is how far away from the axis. Now, the equations that are down here, we've yet to explain. That'll be on another slide. But if I look at B and C, those two are good to compare because one of them has the axis going right through one of the rods. And this one also has it going right through one of the rods. So those should have a pretty low center of moment of inertia, right? But if I compare those two, C has most of the mass is all kind of within half of a rod's length, right? So this mass is still relatively close to the axis. But if I'm rotating around this axis instead, I'm sorry to go this way, some of this mass is way far away and it's r squared, right? So I would argue that we've got a pretty good reason to say that C should be the smallest. And then maybe B should be next because, you know, it's just got one bit of mass that sticks out further away. If I look at either A or D, well, the axis is off to the side, so all of the other mass will actually get to play. It will get to do something here. We could argue, I think pretty easily, that A has more mass that's far away, right, compared to this one, that same amount of mass is only half the distance away. They both have one stick kind of going out. So we could certainly make an argument that that A has a bigger moment of inertia than D, right? And I think then we would probably want to put these on the other side of here. So I think it should be A, then D, then B, then C, and then the next 1 or 2 pages we'll get back to how you can actually calculate those numbers. I heard a little bit of chatter there. Was that something I should stop for, Jack?
Yeah. So we just have a raised hand. I think Anna.
It's hard to hear you.
So I think Anna's got a hand raised.
Okay, Anna, what's your question?
Yeah, I wanted to ask that when we're doing these calculations, when you say that this object has more mass away from the center of rotation, are we assuming that we're not making the assumption that these objects have like one center of mass, like the mass is concentrated at one point?
Oh, the object does have a center of mass. And if we were looking at its translational motion, then I would say, oh, it's that center of mass is the location. Like if I were to throw this, that center of mass would follow a parabola, right? But it could be rotating too, and the other parts are not going to follow the actual path of a parabola. It'll be kind of a parabola with a little swirly thing added onto it. Okay, so the moment of inertia and the center of mass are not really the same concept. I'm not sure if I'm really addressing your question though. They all have the same center of mass. And I don't know exactly where it is, but I'd say it's approximately, it's got to be somewhere along here, and probably something like this location, because I've got so much mass over here hanging out on the end. One way to tell is where can you balance it. So if I could balance this, it seems to balance at a location right about here. And there are ways to calculate that. But I haven't got an example of that ready, but I can get some examples of that ready for Wednesday, if you would like.
I guess I was kind of like confused what you meant by we have more mass on this side than on that side. Because in my head, when I was looking at this question, I was just thinking about like maybe if I could just guess where the center of mass would be, and then I would say like, okay, so the like for example in B, I would say the center of mass is like further away from the line of like rotation.
Uh-huh.
Yeah.
Oh, okay. Yeah. That won't work for moment of inertia. Because moment of inertia doesn't count mass the same way that center of mass does. Center of mass actually does care whether the mass is to the left or to the right of your coordinate system, but moment of inertia doesn't. So if I look at A is saying I'm rotating this. I'm gonna have to step back for this. I'm rotating it this way. Look at all this mass is 12 inches out. Look at, so I say more mass is farther away than B, which is rotating like this. B has hardly any mass way out here. Just the little tip of this ruler is out there, okay? As I rotate here. And that mass that used to count so much when I was rotating this way, oh, that mass doesn't count very much because it's right on the axis. It's hardly moving at all.
Okay.
Okay, so that's what I mean by mass far away from where you're rotating counts more. And it just has to be far away. If I had more mass down here, my center of mass might actually be here, but I'd still have a big moment of inertia because I'd have all this mass that's far away and swinging around. and I'm surprised I've not knocked out an eye here, but for you guys, I'll do that. But I got my safety glasses, I guess. Does that make sense then?
Yes.
Yeah. So that's what I mean by mass that's further away gets to count more. And there's an organized way to figure out moment of inertia from this definition. And I think this is one of the important things that will help you get one of the homework problems done, is that if we're looking at the moment of inertia of an object that's made up of many distinct parts, and I would argue this is made up of 2 distinct parts, then that would mean I have to just find out what's the moment of inertia of this part and this part for a particular axis, right? And add them together, and that would give me the moment of inertia of the whole thing. And that's wonderful, right? You know, if we were doing this, actually, if we were doing this in the regular classroom, we would do some integrals here, because you can take that mass and think of it as little infinitesimally small bits and add it all up. But because we had to cut a week's worth of material out of the course, that got left on the drawing room floor. But you will do it in Calc 3, and you may do it in mechanics classes further in your education if you're going to be in engineering. So let's do a quick example here. It's kind of worked out, and I want to make sure, oh, it's 10 up. Oh my gosh. That if I've got an object here, and I'm intending for this object to be one in which all of these masses, red M, green M, and blue M, are all attached to, I'll say, a massless rod. And what that really means is I've got a rod whose mass is so much smaller than M and 2M and the other M that it doesn't matter, okay? And I've got them arranged like this. I can say that the moment of inertia of the whole object here is the moment of inertia of the red object, mass times its distance from the axis, plus the moment of inertia of the green object, mass times its smaller distance from the center, and then the blue object, which has double the mass of the others, and it's at 2d squared, and if you add all that up, you'll get 13 times little m times d squared for the moment of inertia there. And now I'm gonna do something that may not seem like it makes a lot of sense, but a lot of times what we want to do is we want to be able to write that as some number, some fraction, times the total mass, times basically, you know, kind of the biggest distance you could be away from the axis. So in this case, I'd want to redefine this as r. I would like to have it in the form of something times mr squared. Okay, so to do that, I have to say, well, the total mass, 1, 2, 3, that total mass is equal to 4 times the little itty bitty mass, and that r, that's equal to 2d. And it works out that I can put this in a form where I is equal to 13/16 of the total mass times r squared. And there's probably a number of reasons for it, but one is if I hand you an object, finding its mass is pretty straightforward. Plunk it on a mass balance and you've got it. Okay, what's kind of the biggest dimension from the axis of rotation? Whip out a ruler and you've got it. And sometimes this factor out front here, which is often a fraction, is called the shape factor, because it takes into account that the thing has a shape to it. It has mass distributed in various locations. So this is a convenient form. It may not seem convenient to you, but it will be in a second, or hopefully it will be, because you know, since we're not doing the integration part, in order to find, say, the center of mass of, the moment of inertia of a disk, or a hoop, or a sphere, or a spherical shell, I would need to do an integral. So this table from your book, table 12.2, is actually really handy because it kind of contains the results of somebody else doing an integral for you. So whenever you have a disk, it's in this handy form where it's a fraction times the total mass times the biggest distance from the axis that's possible here. So for a cylinder compared to a cylindrical hoop is cool because all the mass is at the same large distance away, so it makes sense that that's mr squared. And I wrote here a point mass that is in orbit around some axis has that same form, just total mass times r squared. And a solid sphere, well, it's 2/5 mr squared. Does that make sense? Well, if I compare it to a cylinder, that fraction is smaller. That would sort of mean that more of the mass is closer to the axis. Does that seem like it should be true for a sphere that has the same radius r as a cylinder? Well, yeah, kind of, because it doesn't have quite as much mass that's far out. More of the mass is a little closer as you get to like the, I don't know, the Antarctica and Arctica parts, the Arctic and the Antarctic parts of that sphere. The other side has to do with like rods and things. So if you have a thin rod, if you're rotating around the center, they actually do it in terms of the full length, kind of in the spirit that if it were on the side here, if the axis were on the side, then L would be the longest distance that you could be from the center. And for the purpose of working problems, you may use this. This is on the PSS problem sheet, and it would be on the quiz equation sheet as well. So this is a chart that I want you to be able to use and reference, okay? So we've got 4 minutes to finish. We'll probably finish moment of inertia. We won't get to talk that much about energy, which would help you solve problem 2 on the weekly homework. But that's what office hours are for, I guess. So there's one more thing called the parallel axis theorem. And that says if you know the center of mass of an object on an axis that goes through the center of mass, and for example here, this rod, if it's uniform, has its center of mass in the center, so this would be an example of the moment of inertia through an axis with that goes through the center of mass. And if I want to find the moment of inertia for a different axis that happens to be parallel to the previous one, then all I have to do is add md squared, where d is the distance that the axis has shifted. So in this particular problem, d would be here, and it would be L over 2. So let's see if that works out. For this particular case, if I want the I for the parallel axis about the end, that's moment of inertia for the center of mass, which in this case is 1/12 mL squared, plus the total mass, m times d squared, which is L over 2 squared. So L over 2 squared, that's going to be L squared over 4. So that's going to be mL squared times 1/4. And 1/12 plus 1/4. Doing it in your head. So that'd be 1/12 plus 3/12 is 4/12. So that's equal to 1/3 mL squared, which is exactly what we got. Okay, so that's just something, just a problem on the PSS, and I think maybe the one on the weekly homework also. You might have to use that if you're asked ever to find it off on some weird axis, but you know what the center of mass moment of inertia would be. Okay, all right. Can we squeeze anything in here? Oh, I don't know. We've got like 2 more minutes. So maybe I can just put this problem out there and get you thinking about it. And we'll pick up with this problem next time. I've got basically a picture here from a video that Travis and I took. We set up this little red ramp here. And you can see I've got some stuff up at the top of the ramp. This ruler here is holding back 2 discs This disc, the smaller disc is 500 grams and the bigger disc is 1,000 grams. But other than that, they have the same radius, the same R. And I'm going to use this ruler, and I'm just going to kind of lift up the ruler so that they both can start rolling down the ramp at the same time. Okay, and you know, I'm doing this in the context of something we talked about earlier but haven't really done much with, and that is rotational kinetic energy. Okay, I'm reminding you right now that as these things start rolling, they will have rotational kinetic energy. Okay, and then that total kinetic energy would be the sum of the translational and the rotational kinetic energy. So what I wanted to do, if I had enough time, was to send you off into some breakout rooms to say, hey, if I release those, which one is going to win the race? And I don't think we'll have enough time to do that. But I want you to think about that problem, and I want you to think about the idea that if you're going to do a problem that involves, you know, motion of an object, and you've got kind of a before and an after, that your energy conservation equation was normally something like E, say total mechanical energy if you're in a situation where there's no friction, initial equals final. So that was normally U initial final plus K initial equals U final plus K final. So if you were to take that sort of an approach to a problem, I would say just be sure on those kinetic energy terms that you include rotational kinetic energy, okay? As well as what you might call regular kinetic energy, or what we might call translational kinetic energy. Okay, the regular, the 1/2 mv squared kind, but we also have to take into account the rotational, the 1/2 I omega squared kind. Okay, so I'll put that thought in your head because that might help you get a start on the second homework problem. And we'll pick it up when we get back on Wednesday. Now, I'm going to be hanging out to do office hours afterwards. But I look forward to seeing some of you probably at the beginning of tomorrow's PSS. And I'll see many of you Wednesday as well. And those I don't see Tuesday, I'm sure I'll see Thursday, or you'll check in with somebody then. Okay? All right. Bye, everybody. All right. All right, so Angela and Cassandra, how are you? I'm going to go ahead and stop the recording.